All right, hello class. So this is our last lecture together. Um, it's appropriate that what we're going to talk about today is how molecules translate over large distances. Appropriate in a sense that it gives us some avenue or flight of fancy that we can envision while we are all stuck not translating very far from our positions. Specifically, we're going to think about the process of diffusion, which is a description of how molecules move around in space. We're going to first remind ourselves of a basic model for diffusion, then understand the implications for diffusion on bimolecular rate processes. I'll end up with a brief discussion on more complicated rate expressions, just to kind of give you a very quick survey, or not really survey, but a quick perspective on what else one could understand with the sorts of tools we've built up. And then I'll conclude with a few final remarks and kind of a perspective of where we've gone in this class. Okay, so let's go ahead and delve back in. So diffusion, how molecules get around. What we've noticed is that how molecules move through space really depends on over what timescales we are asking that question. Namely, there are two distinct sorts of regimes that have very different descriptions for that motion. Namely, if I was going to consider a molecule over short times, say times shorter than the typical timescales over which a molecule collides with another molecule, that motion on such short times is ballistic. That is to say that a particle moves with a constant speed. So this is true for times less than this tau collision. And ballistic motion implies that the displacement of a particle over that time is proportional to that time. And that constant of proportionality is the typical speed of a molecule, something that takes us all the way back to the first lecture of this course. Now, what we noted last time was that it doesn't take very long for a molecule, even in the gas phase, where the gas is significantly dilute, has a significantly low density, that even in the gas phase, it doesn't take very long for a molecule to collide with another molecule. That collision, therefore, disrupts that ballistic motion and results in a very different sort of dynamics on longer timescales, on times much longer than that typical collision time. After a molecule has had many such collisions, it, for all intents and purposes, forgets which direction it was initially heading in. Therefore, a reasonable description, first due to Einstein, of the subsequent motion is that of a random walk. That is to say, after many collisions, a molecule is equally likely to be moving to the left or to the right, forward or backward. And thus, by understanding some basic statistical measures of that motion, namely that it is on average not moving anywhere, it has some typical displacement, we can find that, for example, we can define a typical mean squared displacement as being what we found to be proportional to time, where the constant of proportionality is the so-called diffusion constant. Now, this is very different than ballistic motion. The mean squared displacement at long times scales proportional to time. On average, a particle doesn't move anywhere because it's equally likely after many collisions to be moving to the left or to the right. Therefore, a typical displacement as can be computed, for example, by taking the square root of a mean squared displacement, is going to be proportional to the square root of time, which is very slow, much slower than the ballistic time scaling, whereby displacements scale in proportion to time. That square root of time scaling means that I require t squared length times to move comparable distances as I would have needed for simple ballistic motion. For example, if we were to note that in air, a typical diffusion constant turns out to be 0.1 centimeters squared per second. That is something we computed as a mean free path squared, a typical length scale over which a particle moves before colliding, divided by its typical time to collide. That if we note that this is the diffusion constant and ask how long for a molecule to go, say, 1 centimeter in air, well, that time goes proportional to the distance squared, so 1 centimeter squared divided by 6 times the diffusion constant. For a molecule to move 1 centimeter in air requires about a second. This diffusive motion is thus incredibly slow relative to ballistic motion. We noted all the way back in that first lecture that a typical speed of a molecule is a football field per second, about 100 meters per second. Rather than moving 100 meters in a second, because of collisions, because molecules run into each other, that motion is slowed to only moving a centimeter over a second. What's more is if I increase that displacement to ask for the time to move, say, a meter, well, that's 2 orders of magnitude larger in length. There's 100 centimeters in a meter. But because there's a squared relationship between time and space in diffusion, that then requires 10 to the 4 seconds for a molecule to move a meter. Or to move 100 meters requires times of years, would be 10 to the 8 seconds. It's a very long time. So again, this is because molecules collide with each other, motion gets randomized and thus diffusive. In air, however, diffusion constants are relatively still large. A molecule can translate a meter. It just takes a while. If I ask for the corresponding motion in a liquid, for example, typical diffusion constants are about 4 orders of magnitude smaller, or on the order of 10 to the minus 5 centimeters squared per second. That's about the diffusion constant of a water molecule in its liquid. If I ask analogous questions like how long does it take for a water molecule or any small molecule to move across a cell, something we think of as a microscopic object. Well, a typical cell, I can draw like so, has some nucleus, has a typical extent, say, of 10 micrometers, which is about 10 to the minus 3 centimeters. If I started a small molecule over on one side of that cell and let it diffuse, how long do I have to wait to translate to diffuse 10 micrometers? Well, again, the calculation goes like time is proportional to the length squared. That's 10 to the minus 3 centimeters quantity squared divided by 6 times 10 to the minus 5 centimeters squared per second takes about 10 milliseconds, or 0.01 seconds. That's a macroscopic time to move a microscopic distance. And that's, again, because in a liquid, density is higher, there are many more collisions, many more randomizations events for that ballistic motion to become damped. And as a consequence, the timescales for that diffusive motion are significantly longer. Now, if you actually looked at that molecule as it's undergoing diffusion, it's a bunch of random hops in different directions. What one finds is that the patterns that the molecule forms on these larger scales, the patterns of its motion on larger scales, look the same as they do on smaller scales. So if we zoomed in to a piece of that trajectory, looked at it more carefully, we would find that the trajectory generated looks comparable. That is to say that the trajectories that a particle traces out as it undergoes diffusion are scale invariant. Now, we've run across that before. If you all remember, in the context of a very different sort of physical scenario, when we were thinking about fluids at their critical points, if we looked at the domains formed by locally liquid-like regions, those two patterns were exactly at the critical point, scale invariant. There was no characteristic correlation length associated with locally liquid-like regions or locally spin-up regions in the Ising model. Here too, diffusion is found to be scale invariant. It has no characteristic scale. It looks the same when viewed on all different scales, microscopically or macroscopically. There are interesting deep reasons for that that are discussed in more advanced classes in statistical mechanics. For now, it will suffice to take this model for diffusion and understand its implications for bimolecular reactions. Reactions that require two reactants, say A and B, to come together to form some product C. So these are more complicated than the unimolecular reactions we considered initially with transition state theory, in that not only do A and B have to undergo some rare fluctuation to overcome a transition state and therefore react, but they also need to find each other, which itself, through the process of diffusion, might take a long time. So specifically, if we imagine cutting out a little piece of fluid, this is maybe happening in solution. If I imagine a solution which had some amount of A and B diffusing around in it, what I require for a reaction to occur is that A and B get sufficiently close to each other. Let's call that scale R, which lets us define a reaction volume, call it little v of 4 pi over 3 r cubed, which is the volume within which both A and B have to be present in order for a reaction to occur. Or a reaction can only occur if both A and B are close, and specifically within R of each other. So bimolecular processes have this added complexity that not only do molecules have to undergo a rare fluctuation in order to react, but they have to undergo they have to undergo diffusion to first find each other. So let's let K naught be the reaction probability per unit time, provided an adjacent A-B pair. So this is the probability per time given I have A and B close together that a reaction will occur. Then the rate, say the amount of C produced in it with a differential increase in time, is going to be the probability that that reaction occurs per unit time times the probability I have a species A that can react, that's just given by the concentration of A, times the probability that B is within R of A. So a reaction occurs only with the product of probabilities for the reaction to happen per unit time given the adjacent pair. And then the probability to form the pair is the probability I have an A times the probability I have a B within a distance R of A. Let's define that probability of B being within R of A as P sub V. Now, what should that probability depend on? It depends on both the characteristic timescales for reactions which are given by 1 over that rate per time, or 1 over that rate constant. But it also depends on diffusion. Let's actually call that react. A characteristic time for diffusion is given by a length scale that we need to diffuse, in this case R, over that diffusion constant. So P sub V, the probability that I find an A-B pair, given I have an A around, depends on both how fast reactions occur as well as how diffusion occurs. Now there are a couple simplifying limits where we can work that out exactly. So first, in the limit that you put a stir bar in your reaction flask, you increase the motion, the speed at which molecules move through space by explicitly adding energy to stir them around. So you have fast mixing. You aren't waiting for them to find each other. You help them find each other. Alternatively, in the limit that reactions are slow, that's when K naught is much, much smaller than D over R squared. In that limit, the probability to find a B in that reaction volume can be reasonably computed by just knowing the probability there is a B per unit volume times the probability times the volume that it can be in. So this should look a little familiar. This is identical to what you have all just worked out on problem set 11. If I have particles that don't have strong correlations and I put one at the origin, the probability to find another particle in that same volume is just the volume over the little volume over the total volume. If I have n of those solutes, I have n factors of that probability. Okay, so that means that the corresponding rate law for how the concentration of C increases with time I have my K naught, probability per time of the reaction. I have rho A, how much A I have, probability of finding an A, times how much B I have, and this reaction volume. Or defining a bimolecular rate coefficient like such, we would say that this bimolecular rate coefficient is the product of that intrinsic rate, the reactive probability per time given a pair, times that reaction volume V. So again, that's in the limit where you are speeding up the time it takes for two species to find each other by explicit mixing, or because the reaction is so slow that A and B can distribute themselves at equilibrium in some uniform manner. Now, the alternative limit would be the so-called slow mixing limit, where you don't have that stir bar moving around species in solution, or alternatively, when the reaction is very fast. Now, in that limit, the reaction is limited by A and B meeting. The rare fluctuation that A and B have to overcome in order to react once they find each other is sufficiently facile to have occur. What they have to do is wait for that diffusion to actually bring them together. And now in that limit, that bimolecular rate should be independent of K naught. You aren't waiting for the rare fluctuation, you're waiting for them to find each other. If we imagine an initially uniform distribution of B, it's distributed in space as it would be at equilibrium, and imagine turning on a reaction at some time t0, immediately what we would see happen is that that reaction would deplete pairs within R of each other. So you have A and B distributed randomly, you turn on, you allow a reaction to start occurring. Immediately, any pair that is close to each other would react. And then the way the reaction would proceed is by diffusion, slowly restoring some number of pairs to form. Re-emphasizing the idea that what one would be waiting for in this case would be diffusion rather than reaction. So then, with that sort of priming, what should that bimolecular rate coefficient depend on in this case? Well, it has units of length cubed per time. It should depend on the diffusion constants. It should probably also depend on how close A and B have to get to in order for a reaction to occur. So if we were just going to guess based on unit analysis, we might suspect that the bimolecular rate, well, one way to get length cubed per time, reaction volume times 1 over time, would be to multiply a diffusion constant, which has units length squared per time, with something that has units of length. Thing that obviously has units of length is that distance r. That at least would have the right units. It's a naive guess. It turns out not to be so far from the right answer. A careful calculation yields kbi is some coefficients that depend on geometry, imagining that reactions could happen in a radially symmetric manner, times that reaction distance, 4, and then a sum of the diffusion constants for A and B, because in general, they might be different. B and A need not diffuse at the same rate, and what matters then is the sum of their two diffusion constants. So again, this too should look familiar. You just derived that on your problem set 11 as well. So this limit is the so-called diffusion limited reaction, or diffusion controlled reaction. It's what you want to, we'd even say diffusion controlled kinetics. This is what you want to avoid typically synthetically. You don't want to wait around for diffusion, which is slow. You want to stir that solution up such that you can operate that reaction as fast as the intrinsic rate will allow you to. Okay, so that's the implication for diffusion on bimolecular reactivity. I want to end now with a little discussion on more complicated rate laws. So even though we've only introduced two different processes, unimolecular and bimolecular rates, that essentially accounts for nearly all chemistry that happens. Nearly all chemistry, even more complicated reactions, can be constructed as a series of so-called elementary steps. An elementary step are combinations, therefore, are combinations of unimolecular and potentially bimolecular rates. That is to say that even complicated chemistries can be decomposed into a step that is either a unimolecular process or at most often a bimolecular process. Probabilistically, this should make some sense. The probability to have two things come together to react depends on the probability of finding one of those things times the probability of finding another one of those things. If we typically work under dilute solution conditions, the probability of finding two things localized in space is already small. If we wanted to have a reaction that proceeds through a three-body process, well, then I'd have to have the probability of finding body 1 times the probability of finding body 2 times the probability of finding body 3, all co-localized in some region of space, which is going to, under dilute solution conditions, is going to be very, very unlikely. This is why overwhelmingly chemistry proceeds through some combination of unimolecular and bimolecular processes. However, That doesn't mean that there aren't sophisticated or complicated things that can still happen as a result of combinations of unimolecular and bimolecular processes. So if we revisited the example we started this discussion with, isocyanide isomerizing to form acetonitrile. If we imagine that happening in the gas phase, and let's label this as the reactant, this is the product, that certainly looks, through the stoichiometry of the reaction I've just written, as a unimolecular process. We envisioned a transition state theory whereby we define some reaction coordinate based on that tilting angle of the cyano group. Imagine having to just wait for a rare fluctuation in order to observe that isomerization. However, it's actually observed at sufficiently low densities of A, so a very dilute vapor of isocyanide, that the rate of change, the rate of increase in B with time is proportional to the density of A squared. Now that's not what you would have expected just by seeing the stoichiometry. I only require, naively, one molecule to undergo that rare fluctuation and thus form B, and yet at low densities in the vapor, chemical kinetic analysis suggests that it's a second order process, suggesting that isomerization is not an elementary step. So that's a little peculiar. How would that actually then work? So it turns out this is something that a physical chemist by the name of Lindemann worked out long ago. He was a physical chemist working in England at the turn of the 20th century, studying this process. He suggested that what happens must be that an A, or initial reactant, interacts with some species M, and with some rate K1 forms what he described as a collisionally excited species, plus that molecule M again. And of course, the opposite is also true, that M could react with that A star, that's collisionally excited A, de-exciting it, returning the initial reactant A. So this M with some other gas molecule that Lindemann postulated was required to collide into A, exciting it, and then only subsequent to excitation, say with some rate K2, could A proceed into B. So what was required was a rare fluctuation in that another molecule had to go give some amount of energy to excite A into this intermediate A star, which then could proceed to react or isomerize. That is to say that the rare fluctuation one was required to see was sufficiently difficult if an A was left by itself. However, that energy could only come, when thought, from another molecule running into our reactant. Now, if that was true, this intermediate A star would build up in time. Eventually level off. And stick around at some steady state concentration. M's floating around, running into A's, exciting them, A's then finding other M's to de-excite. These processes, imagined were occurring at some rate, could generate a population of excited A molecules. And if we imagine that that concentration was constant, it reached a steady state, by writing down the time-dependent rates, the time dependence for the concentration of species A as a loss, as a gain from A and M interacting with rate K1, and a loss from A star interacting with M with K1 prime, and another loss to B with rate K2, that at steady state, the rate of change of concentration of the collisionally excited molecules would be 0, and thus one could solve for that steady state concentration, giving a product of K1 rho A rho M over K1 prime rho M plus K2. And now, if there was some steady state concentration of this hypothetical intermediate, the rate from A to B would then be the rate of change of B equal to K2 times that intermediate, if that had a stationary concentration that we just solved for. I would then have K2, K1, rho M, rho A over K1 prime rho M plus K2. That would be the overall rate constant for forming B from one equivalent of A. Now that's a pretty complicated expression if we thought about its limits. Well, first, in the limit that rho M is very, very large, much larger than K2 over K1 prime, we take a limit of rho M being very large, we can neglect K2, the rho M's then cancel, we'd have a rate for forming B, which was just K1 over K1 prime times K2 rho A. That K1 over K1 prime is just a ratio of the forward to reverse rates of creating or de-exciting rho A star. This is nothing but the equilibrium probability that A is excited. Which is then thus just proportional to rho A. So the rate in this limit where there are lots of these hypothetical M molecules going around exciting A's, in the limit that there's a lot of them, the rate indeed for forming B is just the probability I find that rare fluctuation, I get A excited, times some intrinsic isomerization rate, K2, for A star to go to A, and then it is first order in the concentration of A. However, in the alternative limit, where rho m is small, if rho m is small from this expression, we can neglect it and the denominator. We'll have a ratio of K2s, which cancel. We'll have a K1 times a rho m. So in this case, we have K1, rho m, rho a. Now, what on earth could these m's be? If we envision that actually the only thing in our vapor is other reactants, so we just have a solution, a gas of reactants, they too will collide into each other if what is required for this reaction to occur is one of these, is two of these reactant molecules coming in and colliding to form this collisionally induced excited state, then indeed what we would find is that the rate to form B scales like rho A squared. So physically, what this is saying is that if I have a molecule in the gas phase, if it doesn't collide with anything, it's quite hard for it to overcome barriers, because to do so requires energy, and that energy has no source or sink other than collisions. So in fact, in order to gain enough energy in that molecule such that barriers could be overcome, requires a collision, and thus, if all I have are reactants in my gas, I have no other gas that could serve as a source of that energy, even something that nominally looks like a first order process could scale like a bimolecular process. Now, we invoked through a bit of sleight of hand this relationship here, K1 over K1 prime. That's actually quite a general statement of something called detailed balance. If I have any pair of reaction A going to B with rates K1 or K1 prime, the rate of change of A, well, it gets lost with rate K1, it gets gained with rate K1 prime times the concentration of B. At equilibrium, when the macroscopic density has stopped changing, that rate of change is thus 0. Rearranging then, I have rho A over rho B is going to be equal to K1 prime over K1. Namely, that at equilibrium, the concentrations of species that can interconvert are given, their relative concentrations are given by their relative rates. Now, we know something more than that. We know that the relative concentrations of two species are also determined by thermodynamics. That's given by the free energy difference between A and B. Thus, we've kind of come full circle. We found that even fundamentally dynamic quantities like the rates of reactions are constrained by the laws of thermodynamics. I can't convert A to B without having a rate that goes in reverse from B to A, and I can't choose those independently. It must be, for thermodynamic consistency, that the relative rates are given by the free energy difference, because if the system comes to equilibrium, those relative concentrations have to also be proportional to their changes in free energy. So maybe a more poetic way to make this statement of so-called detailed balance is that all things that go forward must return. Or must be able to return. Okay, well, that's really the last thing I wanted to tell you. If we took a step back, it really is pretty amazing what we've been able to cover in this class. We started at a very basic level, making a very specific assumption. All the way back in the beginning, we made a fundamental assertion that in an isolated system, or all things being equal, our ignorance is taken as a way of saying that all things should be equally likely. If we know nothing else, let's assume that anything that can happen is just as likely as anything else. That was sharpened in the context of molecules by saying in an isolated system, all microstates, if I gave you all of the gory details of some molecular system, all the positions and all the velocities, the whole wave function, that I can tell you what the probability of seeing that microstate was. That probability of observing that microstate is just a constant. All things are equally likely. That constant then just counts up how many things can happen. Now this quantity here, W, the number of microstates from Boltzmann, gave us an entry into macroscopic phenomena. Namely, Boltzmann uncovered for us what was otherwise a fairly abstract notion that had been whispered in the context of thermodynamics. Namely, Boltzmann told us that the entropy of a system is nothing but this multiplicity, nothing but the number of microstates. If you can count, you can predict, if you can count, you know the entropy of the system, you can predict what things happen spontaneously, how much heat is given off in a process, etc. This gave us a concrete foothold into thermodynamics, the accounting of how macroscopic systems change. And that led us to a concrete discussion of the first and second laws of thermodynamics. Namely, the first law, a bookkeeping law telling us how energies change if we make small changes to the system. There we learned that there are fundamentally two different kinds of processes. Namely, work, which are processes that we control. We add a force and cause a corresponding displacement. We add a pressure and change the volume. And the other way that energies can change is through heat. And those are the processes through microscopic chaotic motion we don't control. If we could put our hands on every single molecule in the system, we would never lose any energy to heat. But such a procedure is, of course, practically impossible. We also formulated a probabilistic statement of the second law. From Boltzmann telling us that entropy is nothing but the multiplicity, the number of ways things can happen, we can make a statistical inference that the more ways something can happen, the more likely it is. Therefore, it is intuitive to state that improbable states are likely to become or transform into more probable states. Once we know that entropy is nothing but a reflection of that probability, the statement that entropy increases in a spontaneous process is nothing but the statement that improbable becomes more probable. If I ask for the probability of putting every particle in the room you're sitting in right now up into a corner, well, that's very unlikely. It is much more probable to distribute those molecules equally through space. There are many more ways to do that than there are to put them all in the same place. And thus, if they started up in a corner, it is much more likely that they would fill the room after allowing them to come to equilibrium. And we formulated fairly sophisticated implications of that basic idea. We considered how molecules spontaneously change their collective patterns in going from one phase to another, or how they rearrange their chemical components to react between, or to transform between reactants to products, or to move between two solutions. We uncovered laws of mass action and Henry's law, laws of solubility that you all had been told existed in introductory chemistry classes, but now you know are the consequences of uncorrelated fluctuations of independent molecules. And finally, in this last little bit of class, we not only worked out what could happen, but we said how fast it happens. We actually worked out theories for how quickly reactions could occur using transition state theory by noting that molecules react slowly, not because they move slowly, but because they have to wait for rare fluctuations to advance them up some free energy or energy curve. So, if this sort of material was interesting to you all, there are many other classes that you can take to learn more. These are often graduate courses or courses in other departments. I teach advanced statistical mechanics that will be given in the fall, 220A, and an even further advanced one in the spring. There are plenty of other references that I'd be happy to give you, but I will close by bringing this back over here. Let me stop sharing my screen and say a few words in person. So I know you haven't seen me in a while. It's been a long couple months of quarantine. No, I'm just joking. I didn't grow that big of a bushy beard. But I wanted to say, just on a personal note, it's been really an incredibly memorable and impactful experience for myself to try to teach you all in this world that we're living in right now. It's an incredible thing to ask you all to learn physical chemistry with everything that's happening. And so it means a tremendous amount to me to see all of your efforts persisting. So it's been invaluable, and I'll never forget this semester. You all will have important place in my memory. This class, I think, is not one I'll forget. So thank you all for all of your work, for all of your continued patience with us adapting to these difficult times. And I wish you luck in the midterm. For those graduating seniors, or for the final, for those graduating seniors, good luck in your next steps as you graduate and go do exciting things. And for those underclassmen, hopefully I'll see you in another class soon. Okay.